All right, we are going here, so let's get started. So I'm going to have you guys take a look at a little physics-inspired story problem here. It's pretty easy, but it's going to lead us into what we're talking about today. So let's say we have a car. Say we have a car that travels 60 miles per hour, constant speed, for 2 hours. How far has the car traveled? Don't overthink it. It's going 60 miles per hour for 2 hours. I showed you that video, right? No. I'll show it later, but not right now. It's funny, though. Anyway, so how far has the car gone? 120 miles. Okay. Now, I don't need to solve it in the following way, but I'm going to just to kind of emphasize a point that's going to help us with some stuff later. I can solve this graphically, too. So if I take the velocity of the car as a function, so in this case, it's a constant velocity, so v of t would be simply 60. Okay? And I graph that on a coordinate plane. So this would be the velocity, this would be the time. And then here is 60. It would look something like that, right? And then we said it's for 2 hours. So if I put 2 hours on the time, it's going to hit the function right there. And then it kind of makes this enclosed region here then with the axes. What is the area of that region? 120. Okay, the area of that region and the answer to my question are the same thing. Okay, now doing this for a question like this is kind of stupid because you can do this in your head without needing this. But what if the velocity of the car was not constant? What if it was changing? Would you be able to do it in your head anymore? Not so much. But if I have some kind of a function for my velocity, which I could still do if it was changing, then I could make a graph for that. And then I could try to come up with what the area is underneath that, just like we did here, and get my answer. Okay? Now we're going to come up with some techniques later where we can get exactly what it is. For right now, we're going to just talk about how we can estimate what that area is and kind of think about, this stuff is kind of intuitive, about how we might try to answer that. So let's do another one, and now the car is going to be speeding up instead. I'm just going to give you the equation here. So a car travels with a velocity given by v of t equals 30 plus 0.2t where v is in miles per hour and t is in hours. How far has the car traveled in, let's say, 4 hours for this one? And let's do, we'll do 0.2 t squared. It makes that a little bit more interesting. It does. So, all right. So think about what the graph of this should look like. What is this going to be? It is. It's going to be a parabola. Okay. Now, over here, we had a nice straight line. When we're trying to find areas of things, we like nice straight lines because we can make triangles and rectangles and nice things like that. But I got a curved function this time. It's a parabola. So we have any kind of an equation from geometry to find the area under a parabola? Not so much. Okay. So the best we can do is make an estimation at what's going on this one. So let's try to graph it best we can. And then see if we can come up with a method that might make some sense for estimating the area underneath this one to get the answer to this question. All right, I'll make that just a little bit bigger so you have some room to work with. So it's going to be a parabola that starts up at 30, and then it's 0.2 t squared from there. So let's say this is 30. And then this parabola is going to do maybe something kind of like that. And we want it 0 to 4 hours, so maybe 4 is like somewhere over here. Okay, so we want to get how much is that area in there. So, tell me, what do you think? What would be a good process for trying to break this up and get some area in there? Yeah. Oh, yeah, you guys remember that, don't you? Yeah, okay. Yeah, last year in pre-calc, I think half of you, we got to a point where we were previewing calculus and we actually did this. Okay? So, if you remember that. But anybody else then? What's that? We'll do that in a minute. I just want you to focus on this. If I just asked you, I want you to estimate the area that is in this little region right here, what would you try to do? Okay, so a rectangle, maybe you make a triangle out of it as well, would estimate that thing pretty close. So that particular rectangle right there we can pull out right away, right? So how much area do we have in that rectangle right there? 120, okay. Yeah, that's just a coincidence though. All right, so that's 120. And then I heard the suggestion, what if we make this other piece into a triangle? Okay, so if this is at 30, how tall is that triangle then? Well, how do we know where the top of that thing sits? Plug a 4 into this equation? Okay. So 30 plus 0.2 times 4 squared. Somebody with a calculator, punch that up for us real quick. See what value we get when we have a 4. $33.2. Verification on that? Same thing? 33.2. Okay. So the height of that triangle is 3.2 and the width of it is 4. Yeah? Right, yeah, hold on, let me. Okay, and we're back. So this triangle then has a height of 3.2 and it has a width of 4, so 1/2 base times height. So that should be 6.4. Not drawn to scale, so you know. And then this is this whole triangle here. All right, so if we add those two areas together, we've got 126.4. So our answer is somewhere in the neighborhood of 126.4 miles for that particular car. Okay. Now, looking at the picture, is this an overestimation or an underestimation of what the actual should be? This is a little bit big, right? Because of the concavity of the picture. Okay, this is concave up, so it's going to dip below, making a straight line. So it's going to be, the actual area is going to be a little bit less than what we came up with there. So, the exact answer, so I did it. The actual for this one is 124.3. Okay, so that kind of matches what we have. All right, so it's an estimation. It's pretty close, but it's a little bit above. So now that is one way to estimate. What we're going to focus on with our estimations is doing this RRAM, LRAM, MRAM, which is using some shapes from geometry where we can add together an area. And what these allow us to do is, unlike this method that we did over here, is we can continue to refine, and make it more and more and more accurate. Basically what we're going to do is we're going to chop this picture into a whole bunch of rectangles, and then if we make those rectangles skinnier and skinnier and skinnier, which means we need more of them to cover the picture, we can get a more accurate estimation of what's there. Okay? It's going to be a ton of these skinny little rectangles all sitting right next to each other that we're going to add all those little areas up and then see what we have as an estimation. Okay? So like I said, the more, and this should make sense if you think about it geometrically, the more rectangles you have, the skinnier they have to be, but the more accurate that estimation will be. Does that make sense? We did, half of you did this last year. Right. Yeah, because half of you in pre-calc were able to make it to that chapter 10 section and half of you weren't. So, okay. So let's go through that process then. So how do we do that? Let's start with a simple function to flush this out with. Let's just do x squared. Okay? So we're going to look at a parabola again, but we're just going to stick with regular x squared when we're looking at these different methods for doing it. So, okay. So here's RRAM. Let's say that I want to go from 0 to 2. Okay. With each one of these. Okay, so our parabola, that's really fuzzy. So we're looking for that area under the curve x squared. Stands for is not incorrect, but right as in the right side. And so we're going to make some rectangles in here. And the tops of those rectangles, the top right corner of each one of those rectangles should be touching the function. Okay? So then, what things do you want to make? Okay? And that information will be given to you in the problem that you're working on. How accurate do you want to be with it? Okay? So let's say for this one, we'll go with 4 rectangles. If I'm going with 4 rectangles, how wide are each of the rectangles then? A half. Okay? So that means I need to take my x scale and I need to break it up by half. So 1, 1.5, 0.5. Here. corner of each one of them then. Okay, we'll be using the area of these 4 rectangles to estimate the area under that curve. Okay, now 4 is a pretty small number of rectangles, really, for doing this. Okay, you see why? It's not maybe such a hot idea in practice to just use 4. Does that area look terribly accurate? Not so much. It's definitely an overestimation again, right, on this one? We've got extra rectangle above the curve, so it's not going to be great. You can still do it. Okay. So, basically, we need to figure out how tall is each rectangle. We know the width of each rectangle, right? We just need the height of each one of them, and then add all of that together. Okay. So, that's kind of the formula for doing it. Now, if you take a look there, see how each one of the terms in here has a 0.5, right? Because each one of the rectangles is the same width. It's a uniform width with each one of them. Well, to save yourself some work, factor that out. And you get this. And this is how you guys are going to be doing this in practice. Okay? No matter how many rectangles you have, this will always work. Okay? Whatever the width of the rectangle is, you got to figure that out first. But whatever that width is, that gets multiplied in front, and then it's the height of each one of those rectangles that you're adding together. Okay? And notice when you're doing an RAM, because you want the right corner of each one of those rectangles that you're adding together, you don't use f of 0. You start at f of 0.5. At least in this case, you start at 0.5, because that's the first width that you start with. Because that's the first right corner. So 0.5, 1, 1.5, and 2. So figure out what each one of these are, add them all up, multiply by 0.5. So let's see what that is. F of 0.25. Remember, it's just x squared is the function, right? So we're just plugging those numbers into x squared. F of 1 would be 1. F of 1.5, that comes out to 2.25. And f of 2, 2 squared, 4. All right, crunch the numbers on that, and we end up with 3.75. So that's our estimation for the area under that curve using the RAM method. Now, there's RAM and there's also LRAM. What do you suppose LRAM stands for? Left rectangle area method. Okay. So we're going to do that as well. And think about this for a second. If LRAM, is LRAM going to be an overestimation or an underestimation? It'll be under, because we're using the left corner of every rectangle to add it all up. Okay? So RAM by itself overestimates a little bit. LRAM by itself underestimates a little bit. So what do you think we could do with those two answers? Take the average. And it tends to be a pretty decent indicator of what the actual area is. So that's what we're going to do. So let's do a little LRAM here, though, on the same one. Alright, so we'll draw the same graph here to help us out. Still going to do 4 rectangles again. need to go by 0.5s here then. Alright, so the very first rectangle, we're going to start on the left here. Okay, so the left endpoint touches the function. Do you see how the first rectangle really doesn't even exist here? It has no height. So it's just this flat nothing. And then it's only the second rectangle that we can start to piece things together here. So there's that one, and then the next one will come off like this, and then the last one will come up and over like that. So using LRAM, it's going to look something like that. Technically only 3 rectangles, though. There's going to be 4 things added. One of them is just going to be 0. So this area, 0.5. Start with f of 0, though, because technically that's the left endpoint here. So f of 0 plus f of 0.5 plus f of 1 plus f of 1.5. And notice how we don't use f of 2 this time. We don't use the right endpoint of the interval because we're not including that as part of the last rectangle. Okay? F of 1.5 indicates how tall that last rectangle is, not f of 2. So we don't need it. So let's actually crunch the numbers on these. So f of 0 is, like we said, 0. That's why this rectangle has no height. F of 0.5, again, is 0.25. F of 1 is 1. F of 1.5 is 2.25. So if we add all that together and then multiply by 0.5, we should get 1.75. Okay, so 2 vastly different numbers there. And again, it's a product of the fact that we made our rectangles pretty up here. In practice, like if you were actually going to use just LRAM or just RRAM by itself to estimate the area of this curve, I'd probably use something more on the order of like 8 or maybe 16 rectangles in there to do it. Maybe quite a bit more accurate because you have a lot of extra space both ways on this. Okay. But, like we said, if you average these 2 answers, though, that tends to be somewhat accurate. Even with 4 rectangles, it's not perfect, but it's going to be decently close. And thankfully, we've got 2 answers here that's very easy to take the average of. What's the average of those 2 numbers? 2.75. Okay. Okay. So, we're thinking the area under the curve x squared from 0 to 2 should be somewhere close to 2.75. And again, I know how to do that on my calculator and get it exact, which you will learn later. And that is 2.6 repeating. So, fairly close. Not too bad. 2.75 versus 2.6 bar. That's pretty good. All right, so that's the RRAM and the LRAM. Like I said, I was just using an easy example to show you how those both work. We also have this thing called MRAM, which instead of right rectangle or left rectangle, this is midpoint rectangle area method. It's a little bit more difficult to set up. Highly recommend drawing a picture when you do this one, if you have to do it. But I'll show you how that one works too. And then we'll do some more practice with this stuff, doing a little LRAM, RRAM, some MRAM, with some functions that are a little bit more tricky. Okay. Let's get this one out there. Okay, so we'll go back to our same one again here, just so we can get this one out there a little bit easier. So again, we're going for this area under the curve, but we're going to go using midpoints instead. Still want to do 4 rectangles, so we're going to keep that everything else the same. So we're still going 4 rectangles. So we're going to chop things up like that. But now instead of using the left, like the top left corner or the top right corner of the rectangle is going to intersect the curve of the function right at the midpoint of the top of the rectangle. Okay? So it kind of comes up and then slices through the function, but right at the middle of each of those. So I'll start over on the right-hand side because it's easier to see, but this rectangle is going to come up, and it's not going to come all the way up to this point, but it's going to come over. So right at its midpoint, crossing. Okay, so boom, 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 boom. All of them are right at the midpoint of the top of those rectangles. And the nice thing is, we know those is exactly halfway. So the width of each one of these rectangles is 0.5. But we're not going to go like f of 0, f of 0.5, f of 1. We're doing f of what to begin with? What's the first x value that's going to help us to determine the height of that first rectangle? I think I heard somebody just whisper it. 0.25. It's halfway in between 0 and 0.5. So 0.25. And the next one would be what? So if this was 0.25, what's this here? 0.75. And the next one? 1.25. And the last one? 1.75. Yep. So that's the calculation you're going to use to do an MRAM. Okay? So wherever those intervals are broken up, it's all the points that are exactly halfway in between those. 1.25, 1.75. So what do we get when we... So 0.25 squared. 0.75 squared. 0.65. 1.25 squared is 60. And 1.7 squared, 3.062. All right. So if we add all of the 0.5, here's what you get. .75. What do you notice? It's the same as the average from the other two. And geometrically, if you look at the graph, that should make a little bit of sense. Remember how the MRAM was all that the RRAM was overestimating, the LRAM was underestimating, and then there were pieces that kind of canceled each other out. Well, this one has that same thing. See how each one of these individual intervals has a little piece that kind of cancels a bit of another piece that goes with it. And that amount of what cancels what is the same as what you were doing with the RRAM and the LRAM. Basically, you've got this idea. MRAM is equal to RRAM plus LRAM divided by 2. It is the average of those two. Add them up, divide by 2. So if you're told to simply estimate the area, and you're not instructed as to which method to use, you kind of have two options. If you think just doing this once MRAM thing is easier, do that. Or if you'd rather do RRAM and LRAM because I don't have to try and think about what's halfway in between and mess with all of that, and I don't mind doing it twice and just taking the average, you can do that too. Both will give you exactly the same answer with that. Okay? So, let's practice this a little bit. Okay? Doing some RRAM, LRAM, MRAM with some other functions, and we'll change the number of rectangles and that sort of thing. You guys can still hang with it here. Area under the curve, f of x equals e to the x plus 2 from x equals 1 to x equals 3 using, let's do, all right, so estimate the area under the curve f of x equals e to the x plus 2 to x equals 3 using 8 subintervals. Okay, so 8 subintervals. Think about what that means. A subinterval is an interval within an interval because 1 to 3 is your interval, right? From this to that, that's where we want the area underneath this thing. So that means I have to chop that up into 8 pieces, which means 8 rectangles, right? So we got to think about, what do we need? Numbers do I need to calculate into this function to do it? Okay, so we'll do an RRAM and an LRAM for this. Take the average. We'll do it that way. Okay, so if I'm going to do the RRAM, the right rectangle area method, well, it's going to be that number that sits in front that I'm going to be multiplying everything by this time. 0.25. Right. If there are 8 subintervals and the width of that original interval is 2, then each one of the subintervals is going to be 0.25 in width. So that's going to be what I want there. Okay, and then where do I have to evaluate the function from? Well, if it's an RRAM, remember I'm doing the right corner. We'll do an f of 3 eventually, but I got to start at 1.25. I don't start at 1 with RRAM. So it's going to be f of 1.25 plus, what would be the next one? 0.25 then? Because my width of my interval is 0.25, plus f of 1.75, plus, you get the idea, etc., until you get to f of 3. So we're going to kind of follow that pattern this time then, okay, to get the RRAM. All right, so calculators at the ready. You can do a little bit of rounding. It's not a big. The e to the x, you're going to get huge decimals and that sort of thing. So you've got to do a lot of evaluating. So this is the part of it that can get kind of tedious, but as long as you got the process down, that's good. So e to the 1.25 plus 2. I'll do the first couple for you, and then I'm going to let you guys finish it on your own. 3 decimal places, I think that'll be pretty good. So the first one was 490. F of 1.5 is going to get me 6.482. And then 1.75, 7.755. Okay, so decimal I'll leave it to you. I'll freeze it. I'll do the same thing, and we'll see if we end up in the same place here. But keep evaluating, crunch your numbers. Let's see what we end up with here for this one. Yeah. Yeah. You did? Let me try it once. Yeah, I'm getting the same thing. I'll come back to that in a minute. Get an answer for the RAM for this one? Yeah. Should be 23.129 somewhere-ish. I rounded, so are we in the ballpark? Okay. Now, I said we were going to do RAM and LRAM and then average them. Now, if you have all the numbers written down like I do here for RAM, LRAM's actually not so bad because you're going to have a lot of the same numbers in this calculation, right? If we're plugging in a lot of the same numbers, there's only a couple that change. So the LRAM, we know we want to use the first number, so f of 1. And then we keep going f of 1.25, f of 1.5, until we get to what would be our last one for this. Right. Take a look up here. Haven't you already evaluated every number from 1.25 to 2.75? The only one you haven't done yet is f of 1 that we would need to add to the list. But a lot of those numbers are going to remain the same. So you don't have to go back and plug them all back in again. So it's 0.25 F of 1, just do that real quick. So that would be E plus 2. That's 4.718. Okay, and then we can go up and just start stealing numbers from up here. 5.490 plus 6.482 plus 7.755 plus 9.389. The only number I'm not going to steal from that list up top. The very last one, right, the 20.086. I don't want that one. So the LRAM is going to look like that then. Okay? Do an F of 1, but don't do an F of 3. Add all that together. Okay, so let's figure that out real quick. Alright, so you can double check me, but I got 19.287. Perfect. And then the average should bring us pretty close to our answer here. So 19.287 plus 23.129 divided by 2. To the average, we're getting 21.208. Let's compare that to the actual, which I can do here real fast. So this was what? E to the x plus 2 from 1 to 3. The actual 21.367. So pretty good. Now this one, we got very close. Why did we get very close? We did 8 rectangles instead of 4. Okay? The more rectangles you do, the more accurate the measurement is going to be. Okay? All right. One more here. I think we're probably good. And then Rachel, I'll see if I can come back to this other MRAM that apparently got a different answer there. Let's see. That's not very symmetric. Okay. Let's see, this goes up 2 in a little bit. It's right there. What we're going to be doing is we're going to be taking this idea of area, and we're going to find volume here. See if we got time to complete it. But what we're going to do is we're going to find volume of a nose cone to a plane. Let's say the curvature of the nose cone of this plane is the square root of x. Okay, so that's why I put it in here. So square root of x. Just the whole nose as we go. This thing into a bunch of rectangles, I'm going to partition this thing into a bunch of disks. Okay, so they're going to look like rectangles from the side, but they'll be rotated around and made into these disks. So, and we'll do, I don't know, let's just do 4 of them, I guess, to keep it simple. And let's say this comes out to 2 again. together, but the idea. So the discs are going to end up being just a little bit bigger than the actual nose cone, but my picture actually there isn't real great, but next to each other, okay? It's going to estimate the area of this. So I've got each one of the terms, I'm going to have a pi and a 0.5, right? So I could pull that out front. So it's 0.5 pi. But then I have to do f of x squared plus f squared because of the formula, the way that. And what numbers am I going to be plugging into f of x each time? If I'm doing this midpoint way of doing it. What's halfway in between each one of those? 0.25 would be the first one. Oops, so this would be f of 0.25 squared. Okay, so now we got a formula we can use to actually do a little estimation on volume for this thing. Okay, just pulling out that part that's that's the part that's the same. We still factor out, and then whatever's left over, that we got to add all of that together. Okay. About this for a second before you take out your calculator. Here, 0.25 we actually want to add together then, okay? Because they've been square rooted but squared. So let's see what we get. So 0.5 times 0.25 plus 0.75 plus 1.25 plus 1.75. So we get a volume of about 6.283, and I didn't tell you units, so that should be units cubed on that one. Okay, so that's the idea. I think you have at least one that's like that in your homework where you have to do a volume type of a thing using some disks, but that's okay. This is the crucial point here, right? Setting this up and pulling that into a similar type formula that you can do. And it might tell you use RRAM, LRAM, it might tell you use MRAM. I just follow the directions on that one, but that's the idea. Okay, I'm going to stop recording there, and then